Welcome to section 2.3, additional displays of quantitative data. So we're going to look at different ways to display our quantitative data besides our frequency histogram and relative frequency histogram. And the first one we're going to look at is called a frequency polygon. And essentially we're going to draw a dot in the middle of our histogram bars and then connect the dots. All right, so when we draw a dot in the middle of a histogram bar, that's actually the class midpoint. And how we find the class midpoint is we add up two consecutive lower class limits. So for instance, if we go down to this example, jump down there, the two consecutive lower class limits, one example is 670 and 680. We add those up and divide by 2. So it's like taking the average or the mean. So now frequency polygon uses those points and the frequencies for the height. And then they connect all those dots by line segments. Okay, so there's the formal definition. You guys can read that on your own. The important part, and a lot of students get this wrong, is after we draw our class midpoints and use the frequency for the height and connect all the dots, we need two more lines. We're going to connect the whole graph to the horizontal axis. So let's see what this looks like in practice. So we're going to look at this example and create a frequency polygon for our following frequency distribution table. And it represents the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. Okay, so if we're making a frequency polygon, so again, directions are important, we need to look at the class midpoints. So how we do the class midpoints again is we add up consecutive lower class limits and divide by 2. So you guys can put that in your calculator, but essentially it's 675. Okay, let me talk about a common mistake. A common mistake when I'm asking for a class midpoint is to look at the upper and the lower class limits and add those up and divide by 2, but that's not the definition of the class midpoint. We have to take consecutive lower class limits only. So the class midpoint is 675. Okay, and then to get the next class midpoint, we could definitely add up 680 plus 690 and divide it by 2. If we wanted to work smart and not hard, we would notice that our class width is the same between each classes. So remember our class width, we find it by subtracting consecutive lower class limits, and it's consistently 10. So what we can do to the class midpoint, just based on how algebra works, we can just add 10 to get the next class midpoint. So I think that's a little bit easier than adding up consecutive lower class limits and dividing by 2. So let's just add 10 to get all of our class midpoints. All right, and there you go. And then we have our corresponding frequencies as well. Okay, so if we're going to do a frequency polygon, after we do this, we also have to connect our graph to the horizontal axis, right, which essentially happens at 0. So let's think, one class midpoint before 675, if we're adding 10 this way, we would have to subtract 10. All right, so we're going to have to include this point on our frequency polygon. Likewise, the end of our graph has to get back to the horizontal axis. So we have to think of when the next midpoint is going to be. All right. So again, if you want to write this in, horizontal axis is the class midpoint, and then the vertical axis is the frequency, just like with our histograms. So let's start graphing. So we have to create an x-axis and a y-axis, horizontal, vertical. So vertically we have to go up to 11 just kind of planning ahead. This goes up to 11. And then we have to go 665 to 745, or 1, 2, 3, 4, 5, 6, 7, 8, 9 tick marks. Okay, so with that, let's see if we can get a nice scale. Whoops. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9 things we have to plot horizontally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just made it over here. Okay, so let's fill in our tick marks. And then something like that. If we wanted to label our axes, we could just say this is time between the eruptions horizontally. And let's throw in a unit as well. So time between eruptions is the variable, and the unit is seconds, how we are measuring the variable. And then vertically, we can just call this the frequency. Okay, so let's start plotting our ordered pairs. And I'll do the one in the data set first in green, like I have up there in green as well. So for instance, 675 and 2. And then we have 685, 0, 695, 7, 7059, 715, 9, 725, 11, 735 is 7, and there you go. Okay, so those are the class midpoints. And again, the height is the frequency. So we'll start connecting these dots. No change right there, so it's just horizontal. Okay, and remember with our frequency polygon, we have to start and end at the 0. So we're going to have additional line segments that aren't really part of our data set, connecting us down to our horizontal axis. So a couple notes, even though it looks like our graph is starting right here, our data is starting right here, our data really starts here, all right, just on kind of the definition of what a frequency polygon is. And likewise, it looks like our data set ends here, but it doesn't, right? Because we have zero frequency right here. So that doesn't even include any data points. Our data actually ends here. So a couple things I want to note right now. This is our first class when we're looking at frequency polygons. Likewise, this is our last class when we're looking at frequency polygons. The other thing I want to point out before we look at our next visual display is we can imagine our histogram that we would create using consecutive lower class limits looking something like this, all right? So if we wanted to draw a whoops, that's 0, excuse me. If we wanted to draw a histogram originally, this is what it would be looking like. And we can get it using the heights and the midpoints. Okay, so again, what we're getting from this information is that the class midpoint is right in the middle of the histogram, or the bar of a histogram. We can even work our ways backwards. Let's say we are given just this graph in green. We're given the graph in green. And we know our class width is 10 based on the space between our midpoints. We could find consecutive lower class limits of our histogram bars. So for instance, halfway between 665 and 675 is 670. All right, and then the next lower class limit would be 680, 690, 705, etc., etc. Okay, so we're just gathering information. So why would we do this? Sometimes we're given a frequency polygon, just what we have in green, and we want to know what the class, the upper and lower limit of the class is. So just by looking at the class midpoints, all the class midpoints, we can figure out consecutive lower class limits. And then for instance, our first class right here, we would know that this goes to 670 all the way up to 680, which is the next lower class limit. So the upper limit of the class has to be one less, 679. Whew, that's a lot. Okay, so just to clarify again, the frequency polygon was just this original stuff in green. And then we had some extra bonus rounds in the yellow. All right, so let's look at our next visual display of data. It's going to be called an ogive, but before we look at the ogive, we have to define a cumulative frequency distribution. So again, think cumulative, like our cumulative final at the end of the semester. It's a running total, right? It's everything that we learned before. So a cumulative frequency distribution is an aggregate frequency of the category. So in other words, it's all the number of observations less than or equal to a category. So we're just adding up the sum less than or equal to a number. All right, so let's try this out. So it's the same problem. We're looking at eruption times. And we have our frequency and relative frequency, same data as before, but now we're going to do a cumulative frequency. So what we have to think, in each class, we have to think of the upper class limit. So this is continuous data. So 679 would really include like 679.2 seconds, 679.3 seconds. So really it's anything less than 680. And that's what our cumulative frequency is. It's less than the upper class limit. So how many observations are less than the upper class limit, 680? 2. And that would be our answer for that class. So let's go on to the next class. So the upper class limit is 690. So how many observations are less than 690? Well, 2 from before plus 0. So 2 plus 0 is 2. All right, and then let's keep going. So the cumulative frequency for the third class is everything less than 700. How many observations are less than 700 seconds? 7 plus 0 plus 2. So 9. And then if we wanted to take a shortcut, we could actually just look at 9 plus 9 for the next cumulative frequency. All right, and then 18 plus 9 is 27. So there's 27 observations less than 720. How many observations are less than 730? Well, 27 plus 11. And how many observations are less than 740? Well, 38 plus 7, and it should be all of the observations. And that's exactly what it is, because remember we were looking at 45 observations. So there you go, there's our sample size. Okay, and then as far as the cumulative relative frequencies, you can just take everything from the cumulative frequency and divide it by observation total, and that will get you your cumulative relative frequency. You can also just keep adding up the relative frequency column to get your cumulative relative frequencies. All right, so let's make sure we all have our same answers. however we get it, either dividing your cumulative frequency by 45 or adding up your relative frequencies. All right, and that last category should be 1. So we're going to be doing our ogive next, and we do the ogive based off your cumulative frequency. So ogive is represents the cumulative frequency, or of course cumulative relative frequency. So the time between eruptions is the horizontal axis and the cumulative frequency is the vertical axis. The x-coordinates are the upper class limits. Let's highlight the important parts. The x-coordinates are the upper class limits, and the y-coordinates are the cumulative frequencies. And then we have a line segment joining all of these points, and just one additional line segment is drawn to the horizontal axis at the beginning. And then we don't connect it down at the end. We did that for the frequency polygon. We do not do that for the ogive. All right, so let's hop to it. So we have to go all the way up. Our vertical axis has to go all the way up to 50 this time. All right, so I'm not going to make 50 tick marks. That seems excessive. So I'm going to count by 5s, right? I'm going to count by 5s. So that will be my scale. Okay, so we have again 1, 2, 3, 4, 5, 6, 7 upper class limits, plus we have to connect to the horizontal axis. So we're going to have 8 tick marks here. So the upper class limit of our first class is 680. And then we determined all the other ones. Okay, and then let's see, if we're going to connect to the horizontal axis before the first class, we should write in 670. All right, and again, we label our axes. I kind of ran out of space here, but you can just say time between eruptions, preferably below all the upper class limits. But you guys get the idea. And then we have frequency vertically, and we have to go all the way up to 45. So I'm going to count by 10s. 5, 10, or excuse me, 5s. 15, 20, 25, 30, 35, 40, 45. All right, so let's hop to it. So again, we connect the beginning of the graph to the horizontal axis. And then at 680, we have 2. So we'll just do our best. We'll kind of guesstimate. And then at 690, there's no change, so we still had 2. 700, we had 9. 710, we had 18. 720, we had 27. If you do big dots, you can kind of get away with a little bit more. It looks a little bit more exact. And then 740 is that 45. Okay, and then our final step is we come in and we connect all of our dots. Okay. So there you go. So here we can see rates of change a little bit easier. So that's one of the benefits of our ogives. We can see where we're increasing faster, right? So for instance, when there was essentially a slope of 0 right here, there was no change. And then it looks like we had a steep increase right here. So we know there was a big change in frequencies between those two classes. Okay. Moving on to our final visual display of data. Sometimes our horizontal axis is time. And if we have that kind of data, we can graph it and it will be a time series data. Or it is time series data. When we graph it, it's called time series plot. So time is the horizontal axis and the value of the variable is the vertical axis. And just as before, we do plotted points and then we connect them with line segments. So let's look at this example. Does the growth of New York City appear to be constant over time, or does it fluctuate dramatically? And we have data below, and it represents the change in population over each decade. Okay, so we're going to make a time series graph showing the growth of New York City. And notice that our horizontal axis is time. They're years, right? So it's going to be a time series plot. All right, so let's look at our vertical change. We have to go all the way from negative 0.1 to 3.1. All right, and since we have tenths place, my tick marks are going to be tenths. So that's my thought process on how I'm going to scale my drawing, my graph. Okay. And we're going 1960 to 2010. So 1960, 1970, 80, 90, 2000, and then 2010. Okay, and then let's see, we have to go all the way up to 3. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I did this in 10, so we have like a 1, 2, 3. And then we'll just go 1 down because we need that negative 0.1. Okay, so we can label things like the end of the decade. And then vertically, if you can fit it, you can say change in population in millions. Whoops. I don't know if I can write it. Okay, I don't think I can. So please write change in population in millions on your paper, change in population on your in millions on your paper, just so we have a nice accurate reading. And let's start plotting our ordered pairs. So in 1960, there was 1.9 million change in population. Okay, 1970 was 1.4. 1, 2, 3, 4. There it is. 1980 was negative 0.1. People did not want to live in New York. 1990, it jumped all the way to 2. And then Friends was a huge success, very popular show. So probably everyone wanted to move to New York after that show. And then 2010 was 2.1. So something like this. All right, and then finally, we don't connect to the horizontal axis. We just connect the dots. So something like this. So what do we think? Now that we have a nice visual, remember visuals are very powerful. We can draw conclusions much more easily than just looking at a data set. Do we think that the data, is the growth in New York City appear to be constant over time, or does it fluctuate dramatically? I would say it fluctuates dramatically. And again, we can do that by looking at a visual display of the data.